In these problems, we want to simplify roots that contain both coefficients and variables with powers. We can do this by factoring the inside part, or the radicand. But before we do, I want to review a property with you. We learned that if you took the square root of any base squared, if you assume that a is a non-negative number, then the square root of a squared is just a. And we can extend that to higher powers as well, as long as they're even. So for example, the square root of a to the fourth is a squared, because a squared times a squared equals a to the fourth. So in order to satisfy that, to solve this problem here, first thing you would want to do is factor all of these bases into their prime factors for the coefficient, and then also we want to break down the variable factors into an even power, plus if there's any extras, for example when the power is odd, we're going to break that part out. So it'll look like this: 4 factors into 2 times 2, so we can write that as 2 squared. And then instead of x cubed, you can write that as x squared times x. And then for y to the 6th, since it has an even power, we just leave it. Now we can square root each of these parts that has an even power by taking the power and dividing it by 2. So we would get the square root, we are taking them out of the square root. So the square root of 2 squared would be 2, and the square root of x squared would be x, and the square root of y to the 6th, half the power, would be y cubed. The additional single x that was inside has to stay inside. So that's how you can simplify this first example. It's done. There's nothing further you can do. Let's also look at the second one now. How does this work when the root is not 2? For higher roots, it's the same idea, but this time the property is that you need, in this case, 3 of any factor in order to be able to take the cube root of it. So let's start by factoring 48. If you do a factor tree for 48, you can work it out on the side if you like. 6 times 8, 2 times 3, 4 times 2. I factor down into its primes, and I find that 48 factors down into 2 to the 4th times 3. And then for x to the 17th, we want that power to be a multiple of 3. So what's the closest you can get to 17, but still be a multiple of 3? That would be 15. So we write it as x to the 15 times x squared. Excuse me. And then for the y part, 6 is already a multiple of 3, so we don't have to break it down. And then now we can pull out all of the factors that come in multiples of 3. For 2 to the 4th, I know I can take out 3 of them. That comes out as a 2. And then let me track what's left in here. Excuse me. There would be another 2 left. There's only a single 3 inside of the square root, so I'm going to leave it in there. And then for the x to the 15th, 15 divided by 3 is 5. For the extra x squared, I just leave it in. And for y to the 6th, 6 divided by 3 is 2. So in just cleaning this up, the final answer would be 2x to the 5th y squared times the cube root of 6x squared.
Made with Doodlecast Pro.